Consider a charged particle with a charge q held at rest at the origin of an imaginary coordinate system. If we place a charge q0 at a point P near charge q and release it, then the charge q0 accelerates away from the origin. This acceleration is due to a force on charge q0. Now, let us remove charge q from the origin and reintroduce charge q0 at the same point P. Charge q0 does not accelerate now and remains at rest. This means that the force experienced by q0 is due to charge q. We say that since charge q0 is in the electric field of charge q, it experienced a force. An electric field is a region in which the influence of a charge is felt. Since charge q produces this electric field, this charge is called the source charge. Charge q0 is called a test charge as it is used to study the effect of the electrical field created by charge q. We can use Coulomb's law to calculate the force on q0 due to q. The electrostatic force on q0 due to charge q is F is equal to 1 by 4 pi epsilon naught q q0 by r square into r cap, where r cap is the unit vector along the direction of OP. Let this be equation 1. Now, if q0 is a unit positive charge, that is, q0 is equal to plus 1 coulomb, then the electrostatic force as denoted by equation 1 becomes 1 by 4 pi epsilon naught q by r square into r cap. Let this be equation 2. Equation 2 indicates the electric field strength or intensity of electric field E, which is the force on a unit positive charge acting at a particular point in the electric field. Therefore, the electric field strength due to charge q at point P is E equal to 1 by 4 pi epsilon naught q by r square into r cap. Let this be equation 3. Electric field strength E is a vector quantity pointing in the direction of the force on a unit positive charge at a point in the electric field. In SI, it is measured in Newton per Coulomb or volt per meter. From equations 1 and 3, the force on the charge q0 can now be expressed as F is equal to q0 E. Let this be equation 4. Hence, we can write the electric field strength at P as E is equal to F by q0. Let this be equation 5. The above equation is valid as long as the test charge q0 is very small and its own electric field is negligible. Hence, at point P, we write the electric field strength E as F by q0 limit q0 tending to 0. For a given distance r from the source charge q, the value of 1 by 4 pi epsilon naught is always constant, and hence E, as given by equation 3, will also be constant. Hence, the electric field strength E at any distance r from the source charge q is independent of the test charge q0. It varies with r cap and is inversely proportional to r square. The electric field at any point in the electric field is finite and is 0 only when distance r is equal to infinity. in the electric field of a positively charged particle. The electric field strength vector E at any point in the field always points away from the charged particle in a radially outward direction. The point charge Q0 will be accelerated in the direction of the electric field as it experiences an acceleration A due to the force due to the electric field, and the acceleration is expressed as A is equal to Q0 E by m, where m is the mass of the particle. In the field of a negatively charged particle, the electric field strength vector at any point in the field always points towards the charged particle in a radially inward direction. Here, the point charge Q0 in this electric field will be accelerated in the direction opposite to the electric field. The magnitude of acceleration of Q0 is the same regardless of whether the electric field is due to source charge plus Q or minus Q. For a charge Q, at all points on an imaginary sphere of radius r around it, the electric field strength will be equal in magnitude and will be equal to 1 by 4 pi epsilon naught Q by r square. There is a spherical symmetry with respect to the magnitude of the electric field strength E in the electric field of charge Q.